Right, today we're going to look at section 7.3. As far as the flow of the chapter goes, 7.1 introduced the idea of what a sampling distribution is. 7.2 focused specifically on sampling distributions for proportions. 7.3 is going to focus primarily on sampling distributions for sample means. That's going to be a common structure to several of the chapters we're going to be finishing up the course with. The introduction, how to deal with it with proportions, and then how to deal with the topic with means. Okay, the means have a little bit more going on in terms of stuff we need to know and consider than with proportions. So it's going to take 2 days to get through this section. Today is day 1 of that. All right, so background information here. When we record quantitative variables, we are interested in, something didn't sound right with that. When we record quantitative variables, we're interested in other statistics such as the median or the mean or standard deviation. Sample means are among the most common statistics. Consider the mean household earnings for a sample size of 100. Compare the population distribution on the left with the sampling distribution on the right. What do you notice about the shape, the center, and the spread of each? Okay, so this is the population distribution. Its mean is marked here. It looks like it's, I don't know, in that like 70-ish area. The mean here looks like it would be roughly in that same spot. The shape of this, you would say, would definitely be skewed right. This one here, it appears to be bell-shaped. Perhaps we could classify it as approximately normal. The spread of this is certainly bigger than the spread of that, or at least or you could say the spread of this is less than the spread of that. So those are some general observations comparing the population distribution to the sampling distribution. All right, when we choose many simple random samples from a population, the sampling distribution of the sample mean is centered at the population mean mu and is less spread out than the population distribution. Okay, here are the facts. Suppose that x bar is the mean of a simple random sample of size n drawn from a population with mean mu and standard deviation sigma. The mean of the sampling distribution is the population mean, and the standard deviation is the population standard deviation over the square root of the sample size. And similar to when we were talking about proportions, this is going to be true as long as we're not sampling more than 10% of the total population. Okay, these facts about the mean and standard deviation are true no matter what shape the population distribution has. Or as I had mentioned at the end of the PowerPoint from the previous lesson, you're not going to have to memorize these formulas. The ones that were specific to what we did in section 6.2 were up here when we're talking about sampling distributions for p hat. Now we're doing sampling distributions for x bar. The sampling distribution, the mean of the sampling distribution is equal to population mean. Standard deviation of the sampling distribution is population standard deviation divided by the square root of n. All right, similar to what I had mentioned, this last column doesn't apply to what we're doing in chapter 7. I believe that starts kicking in chapter 8. And in chapter 7, we're only doing the one sample as opposed to 2. We're going to extend those out both for means and proportions in future chapters to include 2 populations rather, not 2 samples. All right, we have described the mean and standard deviation of the sampling distribution of the sample mean x bar, but not its shape. That's because the shape of the distribution depends on the shape of the population distribution. In one important case, there is a simple relationship between the 2 distributions. If the population distribution is normal, and so is the sampling distribution of X bar, no matter what the sample size is. So just rephrasing that kind of back and using some symbols and terminology from the previous slide. Suppose that the population is normally distributed with mean mu and standard deviation sigma, then the sampling distribution of X bar has a normal distribution with mean mu and a standard deviation of this, and that's true as long as the 10% condition is met. All right, so before we get into reading this slide, the important thing is we know if the population distribution is normal, the sampling distribution of X bar is normal regardless of the sample size. Okay, well, what if the initial population isn't normal? I'm going to get into something that's really important to the class, something known as the central limit theorem. Most population distributions are not normal. So what is the shape of the sampling distribution of sample means when the population distribution isn't normal? It is a remarkable fact that as the sample size increases, the distribution of sample means changes its shape. It looks less like that of the population and more like the normal distribution. When the sample size is large enough, the distribution of the sample means is very close to normal, no matter what the shape of the population distribution has, as long as the population has a finite standard deviation. That finite standard deviation, everything we do in this class is a finite standard deviation. That gets way above and beyond the scope of what you need to accomplish if that's not true. So, draw a simple random sample of size n from any population with mean mu and finite standard deviation sigma, the central limit theorem, and it's acceptable to abbreviate by AP rubrics the central limit theorem as CLT. That's considered a universal abbreviation, just like SRS is a universal abbreviation. You're allowed to use it in a free response question. That when n is large, the sampling distribution of the sample mean X bar is approximately normal. Well, so how large is large? Let's take a look at an example here. We have a probability distribution given to us in chart form, given to us in a histogram. Probability histograms for the sampling distribution of X bar for samples of size 3, 10, and 30 are created by a computer to compute the probability of every possible value of X bar. Note that the shapes of the distributions begin to approximate a normal curve as the sample size increases. So this is the population distribution. If we do the sampling distributions with sample size n is equal to 3, this looks relatively close to that. In terms of the quick observation, they're both skewed right. If we increase our sample size to 10, it starts to look less like that and more like a normal shape. By the time we hit size 30, we very much have that bell-shaped curve. So it turns out that 30 is the magic number we're allowed to use. Sometimes you can get that approximately normal shape with sample sizes smaller than 30, but the safe rule of thumb that we're going to be using for this class, regardless of the shape of the population distribution, as long as we're dealing with sample sizes of at least 30, we can assume that the sampling distribution is approximately normal. All right, this is another example to illustrate that idea. So we're starting off, which is a very strange population distribution. Looks like it's trimodal. It's got 3 peaks. Very weird shape. So if we were to approximate the sampling distribution of sample size 2, you see that this resembles somewhat the original population distribution. It's certainly not looking like it's approximately normal. We go up to sample size 5, looking less like that and starting to build that normal shape. Sample size 10, even less like this, more normal. By the time you hit sample size 25, we very much have that bell curve thing going on. And then if we hit the 30, it would be considered close enough in order to approximate it with a normal curve, which means it allows us to use normal CDF. All right, so we're going to add on to what we had said earlier on to include the observations we just made. As the previous examples illustrate, even when the population distribution is non-normal, the sampling distribution of the sample mean often looks approximately normal with sample sizes as small as 25. It can happen with 25, but again, we're going to use 30 as the cutoff number. So, one thing from a few slides ago, if the population distribution is normal, then so is the sampling distribution of X bar. This is true no matter what sample size we have. Second part, if the population distribution is not normal, the central limit theorem tells us that the shape of the sampling distribution of X bar will be approximately normal in most cases if n is greater than or equal to 30. In far as what we do in this class, we can consider the most, we can pretty much replace that with all. And the reason why that's important, the central limit theorem allows us to use the normal probability calculations to answer questions about sample means from many observations, even when the population distribution is not normal. Okay, just as a side note, this is an algebra-based statistics class. Some of you may have to go on in college to take a calculus-based statistics class. If you're in a calculus-based statistics class, that proving the results of the central limit theorem is something that you'll investigate in more detail. We just take it as, yes, it's true, without verifying it or going through why it is. The why it is above the scope of an algebra-based statistics class, but in a calculus-based statistics class, that'll be something that you would examine. All right, back to the PowerPoint. So a little visual to tie these ideas together. Same basic visual we had when we were doing sampling distribution for proportions. You have some population. You're going to take a sample size of size n, calculate its mean, plot it. Take a second sample of size n, calculate that sample mean, plot it. Third sample, size n, calculate the sample mean, plot it, etc., etc. If you were to plot all possible sample means from this population of size n, this distribution would be approximately normal. The mean would equal the population mean. The standard deviation would be the population standard deviation divided by the square root of n, assuming the 10% condition and all that other stuff gets met. All right, some warnings again with vocabulary and some ideas that you want to make sure that you have straight. Don't confuse sampling distribution with the distribution of the sample. Those are two different things. When you take a sample, you look at the distribution of values, usually with a histogram, and you may calculate summary statistics. The sampling distribution is an imaginary collection of the values that the statistic might have taken for all random samples, the one you got and the one you didn't get. We need to watch out for small samples from skewed population. The more skewed the distribution, the larger the sample size we need for the CLT to work. It doesn't necessarily have to be skewed, it's just non-normal. The more non-normal the population distribution is, the larger the sample size we need in order to get that approximately normal. And again, we're going to use the 30 as the universal, regardless of other things that may be going on. The sample size of 30 is considered good enough for what we do. All right, now on to some problems. What types of questions are you expected to answer using this information? Okay, based on the data from the U.S. Census, the mean age of college students in 2008 was 25 years, with a standard deviation of 6.8 years. A simple random sample of 64 students is drawn. What is the probability that the sample mean age of the students is greater than 26 years? All right, the sample size is 64, which is greater than 30, and our sample size is less than total population, therefore we may use the normal curve. Okay, it never said here that the population distribution was approximately normal. Okay, without knowing that this population distribution is approximately normal, in order to answer this question, we have to have a sample size of at least 30, which we do. For the most part, this is a condition for almost everything we do. If we're sampling without replacement, we can't sample more than 10% of the total population. 64 is certainly less than total, 10% then of the total population of college students. So the conditions could be met. The mean of the sampling distribution of X bar is equal to population mean, which is 25. We should have a unit there of years. The standard deviation of the sampling mean, population standard deviation divided by the square root of the sample size, 0.85, and again, that should have a unit of years. So, those are the mean and standard deviation we can use in our normal CDF command. We are looking at the probability of the sample mean age being greater than 26. So, lower bound, upper bound, mean, standard deviation, a little less than a 12% chance that the mean age is greater than 26. Given this information. Okay, another example similar to the one we just did. Hereford cattle are one of the most popular breeds of cattle. They get invited to all the cool cow parties. Anyway, based on data from the Hereford Cattle Society, the mean weight of a 1-year-old Hereford bull is 1,135 pounds, with a standard deviation of 97 pounds. Would it be unusual for the mean weight of 100 head of cattle to be less than 1,100 pounds? So, one thing to take note of as we're reading through these problems is you want to see if they say anything about the shape of the population distribution. The shape of the population distribution is not determined here. It didn't say what it is. But if we have a sample size of at least 30, turns out that it probably doesn't matter what the shape of the population distribution is. So running through the checks to make sure we can use our normal CDF. The sample size is 100, which is greater than a 30, and our sample size is less than 10% of the total population. So the mean of the sampling distribution equals population mean, which is 1135, and that should have a label of pounds. The standard deviation of the sampling distribution is 9.7, and again, that should have a label of pounds. So, we can use our normal CDF. We are looking for unusual for the mean weight of less than 1,100 pounds. So, less than 1,100 pounds, lower bound, upper bound, mean, standard deviation. And we are looking for a percentage of less than 5%, or another way, if you're dealing with a normal curve, which we are, we can do the more than 2 standard deviations away from the mean. More than 2 standard deviations away from the mean, or the less than 5% accomplish the same thing. To be more consistent with what we've done in the past, probably better to concentrate on the 2 standard deviations away from the mean, rather than introducing a different way of describing it. I'm sorry, the less than 5% rather than the 2 standard deviations away from the mean. All right, a couple more examples here. I already filled in the solutions in the interest of time for this video. The weights of newborn children in the United States vary according to the normal distribution, with a mean of 7.5 pounds and a standard deviation of 1.25 pounds. The government classifies a newborn as having low birth weight if the weight is less than 5.5 pounds. So as we read through this, one of the things that we want to be looking for is that right there. If we know the population distribution is normal, or approximately normal, we can use normal CDF regardless of our sample size. Question 1, what is the probability that a baby chosen at random weighs less than 5.5 pounds at birth? Well, whether we're looking at a single individual baby or a group of size n babies, with the population distribution being normal, we can answer this question with normal CDF. So lower bound, upper bound, mean, standard deviation, and we get about 0.0548. Now, just in terms of connecting the real world to what we talk about in statistics, the government classifies a newborn as having a low birth weight if it is less than 5.5 pounds. Well, low birth weight, you can kind of think of that as an unusual event. So an unusual event in our course is around that 5% mark. So kind of ties together there. All right, instead of choosing one baby, what if we chose 3 babies and we compute the mean weight? So now instead of looking at the weight of one individual child, we're looking at the mean weight of a group of 3 children. What are the mean and standard deviation of the sampling distribution of the mean weight of the 3 babies? Well, the mean of the sampling distribution is equal to population mean, which is the 7.5 pounds. The standard deviation of the sampling mean is population standard deviation divided by the square root of the sample size. Population standard deviation, sample size is 3, that's our standard deviation. Okay, what is the probability the average birth weight is less than 5.5 pounds? So we're still looking at a lower bound, upper bound, the same as that. We're still interested, or still have the same mean, the 7.5 pounds, but now our standard deviation is different. That was the standard deviation for choosing 1 from that population. Now choosing a group of 3, it's that number divided by the square root of 3. So 0.0028, that's like 0.2 of, or rounding 0.3 of 1% of a chance. So it's much more unlikely to get 3 babies with a mean birth weight less than 5.5 than 1 single baby with a birth weight of less than 5.5. All right, this is a very common what-if question in the AP world. Would your answers to 1, 2, or 3 be affected if the distribution of birth weights in the population were distinctly non-normal? Well, if we don't have a normal distribution, we certainly can't use normal CDF for 1 single baby from there. So we wouldn't be able to answer number 1. We would have to have a sample size of at least 30 to be able to use this if it's a non-normal distribution. Okay, number 2, the mean of the sampling distribution is always equal to population mean, regardless of shape, regardless of sample size. Okay, this is based on not sampling more than 10% of the total population. Since we're not sampling more than 10% of the total population, that would also remain the same. So those would be the same answer. We can't answer number 3 for the same reason we couldn't answer number 1. If our population distribution is not normal, they're saying that this wasn't there, then we have to have a sample size of at least 30 to be able to answer that question. All right, one more set of problems. Here's our setting. The composite scores of students on the ACT college entrance exam in a recent year has a normal distribution with a mean of 20.4 and a standard deviation of 5.8. Okay, what is the probability that a randomly chosen student scored 24 or higher on the ACT? Well, we're specifically told population distribution is normal, so we can figure out the probability of that 1 student. Same commands we always use. Okay, what are the mean and standard deviation of the average ACT score for a simple random sample of 30 students? Mean of the sampling distribution equals population mean, which is 20.4. Standard deviation of the sampling distribution, population standard deviation divided by the square root of the sample size. Okay, what is the probability the average ACT score for a simple random sample of 30 students is 24 or higher? All right, so here was the probability of 1 person having a score of 24 or higher. Now it's the probability of a group of 30 having an average score of 24 or higher. We still have the same lower bound, same upper bound, same mean, but now the standard deviation is different. That's the standard deviation for that 1 student. This is the standard deviation for a group of 30. So we get a highly unlikely event. It's rounding to almost 0. Right. Would your answers to 1, 2, or 3 be affected if the distribution of ACT scores in the population were distinctly non-normal? All right, well, if it's non-normal, we can't answer this one. We don't have enough information to be able to answer that question. We certainly can't use normal CDF for choosing 1 person or 1 individual from a population that's not normal. Okay, number 2. The mean of the sampling distribution is always equal to the population mean, regardless of shape or sample size. This standard deviation formula is based on not sampling more than 10% of the total population. 30 is certainly not more than 10% of the total population. That'll be the same. Okay, this one here, we do have a sample size of at least 30. So if our sample size is at least 30, it doesn't matter what population standard deviation, or the population shape is rather. We would get that same answer by the central limit theorem. As long as the sample size is at least 30, then our sampling distribution is approximately 1. That is it for today.